about random variables today. There's a few different types. We're going to just focus on one type for today and kind of keep this lesson fairly simple. We're going to be talking about discrete numbers here today. And I want to do a quick review of what that is. If something's discrete, I don't know much about Math 2 or Math 3, but if you go back to Math 1, we talk about discrete. And a discrete graph would look maybe like this, where here's 1, 2, 3, 4. So discrete linear kind of thing. It's not connected. There's no method in the context to allow for like a 1.5 or 1.75 or something like that. It's just the numbers that are given. So we have no decimals or fractions. Beyond what is allowed by the context. So context is key on this. If the context was talking about halves, say for example, then this could be 1/2, and this could be 2 halves, and 3 halves, and 4 halves. Oops, halves. The context could allow for that, but then you couldn't do a quarter, right? Does that make sense? You can't split it up more than what is allowed in the context. So discrete random variable, a discrete random variable, is basically saying pretty much what I just said, where x takes a fixed set of possible values with gaps between them. So whatever the fixed values are, there's gaps between them. So let's look at a scenario that would have gaps between them. How about if we toss a coin 3 times? What's the probability of heads? That's a pretty generic statement of any heads. So if I toss a coin 3 times, I could get 3 heads in a row, right? So a possibility would be head, head, head. Or maybe I get 2 heads. Maybe I could get a head, head, and a tail. But with coins, order is important. So I'm going to have, possibly I could do a head, tail, and a head. Or I could toss a tail, a head, and a head. And that would be the list of all the possible ways that I could flip 3 coins and get 2 heads. Or I could flip 3 coins and get 1 head. So head, tail, tail. Maybe tail, head, tail. And tail, tail, head. And there's one more way that I can flip 3 coins. All tails. Yeah, all tails. Which is no heads at all, right? So what are the probabilities? Well, turns out that there's 8 ways that I can flip 3 coins and get a response. So I have 1 in 8 flips. I can expect 3 heads in a row. 3 in 8, I can expect to get 2 heads. 3 in 8, I can expect to get 1 head. 1 head. And 1 in 8 if I get all tails. And if I add all those fractions up, what do I get? No. 1. 8 out of 8. 1. 8 eighths. Okay. So let's say we do this many, many times. I flip 3 coins and I write down the response and I do it, and I write down the response and I do it, and I write down the response, and how many heads would we expect after many, many trials? What number of heads would we expect? I don't think it's 2. 1.5. You're right. It's 1.5. After many, many trials, the average would be 1.5. But is there any way that I can actually flip and get 1.5 heads? No, because it's discrete. You can only get 3 heads, 2 heads, 1 heads, or no heads. There's no way to get 1.5 heads. This is a discrete, random, variable situation. But the answer would be, after many, many trials, you could get the average of 1.5 heads. 50-50.
Couldn't technically, if it lands like on the edge,
Yeah, that's a what if that has never happened in my classroom and, to my knowledge, anybody else's classroom. Yeah.
The video that you showed us in class had the same pattern as what the coin is. Does that have any relation with each other or no?
The same pattern as the coin. Which video?
It was the first video that you showed us about the problem, learning about what's called the Hall problems.
Oh, the Monty Hall problem?
Yeah.
Where it was the 3 doors?
Yeah, and then you showed us a chart where it was like switch, save, and then they looked like very similar to how you did the heads and tails.
It would be sort of similar to this guy here, right? Yeah. But you have to take into consideration on that, you're picking one. So that's why there's not just 3 ways to do it. You could do this 3 different ways, where you pick door 1, door 2, or door 3. And this could be done 3 different ways, door 1, door 2, door 3, right? But yeah, it is. The Monty Hall problem is very similar to this idea. Sure. So, so the average is 1.5 heads. There's some new notation, or at least new to me. It's new in this book. Notation for expected values. And mu sub head, oops, I don't need parentheses there. Mu of heads would be 1.5. Now, anytime we're talking about mu, we're talking about many, many trials. A population of trials, if you will. Okay? A population, you have to have a population to get that average. Or, this is the new one to me, this big E to the H, equals 1.5. This is expected. I don't know how often that'll come up because I haven't looked through the whole chapter yet, but it's worth noting that this book uses that notation. Either one you might see. And speaking of notation, I'm behind on giving you guys quizzes, so expect a couple of quizzes between now and the final, and it'll be more like symbols kind of things. Okay. Also, we've got a project we need to get you going on. I'll get you probably heading on that later this week. Yeah.
Can you explain the 1.5 heads?
Yeah. So if I took all of these numbers, so this would be 3 heads, and this would be 2 heads, and this would be 1 head, and this would be 0 heads, right? And if I took and averaged this out, 3 happens once in 8, 2 happens 3 times, 1 happens 3 times, and I'm running out of space here, and then 0 happens 1 time. If I took just that and added those up and divided by 8, I should get 1.5, I think. Oh no, where's my calculator here? My calculator's gone. Let's see, 3 plus 2 plus 2 plus 2, let's see, that's 9, 10, 11, 12. 12 divided by 8, 1.5, yeah. So there's no guarantee that you would get it exactly like that if you flipped it 8 times, but that's what we would expect. Good? Okay. Let me rewrite that, because if somebody watches my video, they'll go, what? Okay. So let's look at an example. There's an example in the book. If you're lucky, you won't have to put these numbers in, but it's not all that big. It's talking about APGAR scores. And what an APGAR score is it's a score that newborns are given in its regard to health. How healthy is a newborn? So it's discrete from 0 to 10. So you can't get an 8.5. There's no newborn that's 8.5. It's 8, 9, 10, whatever. So these values are discrete. And what I want you to do is I want you to take and put into L1 your 0 through 10, and put into L2 the probabilities. I'll zoom in as much as I can, but this is on page 367. Yeah, 367. Yeah. L1, 0 through 10. L2, the probabilities that go along with it. Yeah, if you're lucky, it's already there.
Is it 367?
367, yes. Page 367. So if we wanted to find the mean of these, what we would have to do is we'd have to multiply the 0 times the probability, the 1 times the probability, the 2, and so forth, and then take the sum of all that. That would give us our mean score. And on this page, they show that calculation. They don't really give us the formula here, but they show the calculation. But there's a better way, and that's why we're using the calculator. So what I want you to do once you get that in is I want you to go to 1var stats. Remember that one? go to Stat. Hang on, I'm going to quit here. Get back to the main screen. You go to Stat, and then it'll be Calc. And you go to 1-var stats. Now, it seems odd that we would have one variable here, but we really only have one variable. There's one variable in the probability. Now, up to this point, I've told you that leave the frequency of the list blank. And now I know, too, how that works. So what the frequency of the list is, how often does that occur? So that's your probability. So put L1 in for your list and L2 in for your frequency. And calculate. Now what we'll get is our X-bar, our average. And it doesn't give us a standard deviation for the sample, it gives us a population standard deviation. I think the calculator just assumes that we're talking about population values here, which we sort of kind of are. This number, I believe, is slightly different than what the book gives, because the book gives it as a sample value, but it's close enough. Okay? So we're going to use this as our standard deviation, and this is our mean. The mean is correct. The standard deviation is only slightly off. To do the standard deviation properly, that would be on the next page, and you have to do this as a formula. So, no? No, you sure? No takers? Come on, chickens. All right. Yeah, it would take a little while, and it would be likely easy to make a mistake. So, let's write some stuff down here. So our example is on page 367. APGAR scores in children, specifically newborns. So L1 we put in as our values of scores. Keep in mind this is a discrete value. A kid can't get a 1.5 or an 8.5 or a 7.6 or anything like that. L2 was the probability of those scores occurring. And we went to 1-var stats. Our list was L1. Our frequency of the list is L2, and then we calculated. And we got X bar is about 8.128, and sigma X about 1.44.